So we're talking about current, and I give you a wire, and we can let the little blue dots represent electrons and the red dots represent protons. That the wire is full of both. Last year we played around with marbles in a tube that sort of an incompressibility, and that would be because of electrostatic repulsion between the protons and the electrons. But current, of course, has to do with the flow and the flow of charge. That Benjamin Franklin suggested that the thing moving was positive. That we will learn later that we can do experiments to determine that it is in fact the negative that is the thing that is whose motion represents the current. But there's a lot of other motion going on in the wire. That these electrons and protons are going to be moving thermally, and they're going to be moving at about 10 to the 6th meters per second, very, very fast, 100th the speed of light. But this motion would be random, and so the electrons would be moving in all directions with equal likelihood, and so would the protons, and it does not constitute what we're thinking about as a current. If this were a water hose, and we sent water going through it, that would also be a tremendous movement of charge that would go through. You would be having I don't know about that. That these charges would be moving very, very fast. But of course you have both the positive and the negative, so there is no net charge that is moving through the wire. So that would not be what we're talking about when we want to go for a current. That instead the idea is that there is net charge moving through the wire. That if we put a field across the wire, and here's a unique thing that I haven't completely sorted out, but we said that inside of a conductor the field would be zero. But in this case the field is going to be uniformly distributed everywhere in the conductor. So something is different. I think it has to do with a situation of static charge. There would be no field inside of a conductor, but when you have this charge in motion, then there would be field throughout the conductor. And I wish I understood that. Maybe you'll explain it to me. But there would be field everywhere here, and that would of course cause the positive charge to go in the direction of the field. It would cause the negative charge to go the opposite direction, which is in fact what happens. But this would be a net motion. The actual rate of motion when you have a current flowing is on the order of tenths of a millimeter per second. We call it drift velocity. That this thermal motion is still going to be there, and so there's going to be tremendous movement of the charges in all directions. And then layered on top of that, so subtle that you probably would not be able to see it, look at the difference in scale, there is a net drift of the negative charges contrary to the field. And if positive charges could go, there would be a net drift of the positive charges with the field, very, very slow. But this is what the current is, not this thermal motion in the field. So there is the thermal motion. Now, when we talk about current, we're going to pick a point on the wire and look at how much charge goes by it, and this is the rate at which that charge would be moving, but there's tremendous amounts of it in terms of coulombs. The fact that we are moving, and now we're back to marbles in a tube, that once motion starts, it's going to happen everywhere in the wire, and the fact that we're moving again is going to be communicated in the wire at about 1/10 the speed of light. Very quickly, the fact that we're moving here is also happening elsewhere in the wire, that when you throw a switch at one point in the room, all the wires connected to that switch have current flowing in them at this rate. So the fact that there's motion, all the marbles pushing against one another, gets communicated very quickly, but the actual marbles themselves are moving very, very slowly, as constitutes the current. However, the marbles are moving very fast, but in all directions, and that does not constitute a current. Okay, so the symbol for current will be a lowercase I. We used a capital I last year, but we use a lowercase I for the current. We will save a capital I when we were talking about the maximum current. But this is what you're going to see for the most part, and the idea is that you choose a point on the wire. Rather than getting motion as how far it goes in second, we will go how much charge passes that point every second. So the current will be defined this way. Here's a surprise. Current is going to be considered a scalar, and we'll have a lot of fun with that, but the book is very clear. Current is a scalar. It does not have direction. Well, it's not a vector, and yet there is a direction that the current's flowing. I think the problem is that if this was a wire, and you took the wire and orange, and you bent the wire around like that the current flowing through this wire, these would not constitute accelerations. There would not be some force needed to account for this motion along the curved path, even though the direction of the current is changing. And so I think that's the reason why we don't call current a vector. At any rate, its units, of course, would be coulombs per second, which have been renamed an amp. Here you have a nice little problem, and the point of this problem is a sort of that what a current represents is charge moving through the wire, and if let's let it be positive charge carriers. If you have 1 amp's worth of charge carriers going here and 2 amps of charge carriers going there, these are protons, so you must have 3 amps of charge carriers going in. It's a kind of a conservation of matter issue, that you must have as much current going into a junction as coming out of a junction. This is called Kirchhoff's junction rule, and that if here in the wire you had 1 amp's worth moving, then over here in this same wire you would have to have 1 amp's moving, that the current would have to be the same everywhere because there's no junction there. So if you like, there are junctions everywhere, and I'll make a junction for this junction right here. There needs to be as much current going into it as coming out of it, and so that gives you that the current is going to be everywhere the same along a wire without branches. At any rate, you should be able to sleuth out what this current here is based upon the argument that I just used for that junction. And you're done with that problem. Introduce a new idea, current density, current per cross-sectional area flowing through a space. This is a capital J, and in this case, I think the reason it's a capital J is they're trying to use capitals for vector quantities and lowercase for scalars. Yes, an area is a vector quantity. There it is, capital A. So they're consistent about that. That's pretty bizarre. Here you can look at this picture, and you can see the subtle difference here that this one has uniform current density. If you do a cross-sectional area anywhere along here, it's the same current passing through that area. So J, the current density, is uniform here. It is not uniform. It's fairly uniform through here, but here at the ends it becomes non-uniform. I would ask you on your worksheet to indicate what's the difference. Why do you get a uniform field here and a non-uniform field here? And it's fairly obvious, but you give me that. Now, this being a vector means that this side of the equation over here has to be a vector too. But we just asserted that current is a scalar. So the directionality of this current density must come from this area. So here we draw a little bit for you. So I put an area, a cross-sectional area across this wire, and I'm going to look at the current divided by that, but the direction of the area, well, we've worked with areas often enough. The direction of the area is going to be normal to the area. But of course that normal could be drawn in either direction. And so we choose, it's going to be normal to the area, there's the direction, but which way does it go? It goes in the direction that the current is flowing. Even though the current is not a vector quantity, its, in quotes, direction is the direction of this normal vector here, and hence the direction of the current density. And if that sounds awkward, it's meant to. And that completes this lecture.